All right. You're on camera this time because I'm going to be gone later today, so my other classes need the video. So here we go. Be as annoying as possible. All right. Now, here's the thing. Solutions and are really focusing on the idea of concentration. And before we talk about concentration, I like to give an example of things in your life that might help you better understand what concentration actually is. So you know how when you go to the Six Flags or when you go to like the State Fair and they got that lemonade in a cup for like $7, you know what I'm talking about? It's like solid frozen lemonade for $7. As a father, it hurts my soul to purchase a $7 cup of frozen lemonade. It's just not economically responsible, in my opinion. It's the equivalent of leaving the refrigerator door open and cooling the entire neighborhood, right? So what I do is I don't buy those things. I say we got it at home. It's kind of like that meme that's floating around out there where it's like, hey, Ma, can we get McDonald's? And then the picture is like McDonald's at home, which is like a half-eaten cheeseburger from like 4 weeks ago. You know what I'm talking about? No? Okay, all right. But at my at home is actually that frozen concentrated lemonade that you buy at the grocery store. It comes in the can. You peel off the top. You lick it. It's like super sour. You know what I'm talking about? And then you flip it over and it comes out and it's like, and then it comes out and it's like, and then it comes out and it finally makes this sound. And then it lands in the bottom of the container, right? And then you have to add water. And then the container is like, we're going to add 3 1/3 containers of this can. And like, as a chemist, you have to understand that I deal with numbers and precise measurements all of the time. But what is 1/3 of this? I don't understand what 1/3 of that is. Like, I can fill it up 3 times and then it's a guess? Are you kidding me? They don't even put markings on the inside of that cardboard. Like, how am I supposed to do this correctly? I care about the meniscus when I'm worried about putting water into a pot to boil rice. Because you know that once you make that lemonade, you can't unmake the lemonade, right? You can't like take the lemonade and pour it in there. And if it's just too much water, what if you put 3 1/2 instead of 3 1/3? And then it comes out and all of the lemonade is ruined. It's all about proper concentrations, people. And that's why I don't know what to do with myself. And so, of course, we don't actually at my house eat or drink that lemonade as it's made. What we actually do is we sit on the front porch and eat it with a spoon, because that, my friends, is the lemonade in a cup that my family gets, because it's $1, not $7. And you get multiple tries at it because also when you're at the fair or you're at the Six Flags, right? You're like, oh, I'm done with this. I'm going to save it for, you can't save it for later, because it's 97 degrees outside. Anyway, concentration in chemistry is very much like this entire internal dialogue that I have every time I make lemonade at my house. So the issue is that when we talk about things being concentrated, what we're talking about is we're talking about the idea of how much stuff is dissolved in a given amount of water. If something is really highly concentrated, what that means is that you've taken a bunch of solid particles, or maybe not, but in oftentimes solid particles, and you dissolve them in a very specific amount of water. If you want something that is low concentration or very, very dilute, which would be a word that you might use, you would take like itty bitty teeny amounts of that particular substance and dissolve it in the same amount of water. For example, if I took 20 grams of table salt and dissolved it in 100 grams of water, I would have a pretty salty beverage. Okay. But if I take 10 grams of table salt and dissolve it in 100 grams of water, I would have a significantly less salty beverage. 20 grams in 100 grams of water is going to be more concentrated than 10 grams in 100 grams of water. And of course, in chemistry, there's always the thing that we do, which is make our lives a little bit more complicated by adding vocabulary to everything. So in this case, the new vocabulary is the term molarity. Okay. Molarity is a way to show the ratio of stuff dissolved to amount of solvent. okay, or what you're dissolving it in. And of course, there's a formula associated, which is molarity is equal moles of solute over liters of solution. You might see it written like this. Okay, so you might see it written like this. Now, in your life experience, if you're doing a molarity calculation, sometimes you'll be given a mass and you'll have to convert it to moles. So like things to consider. You might have to convert mass, which is grams, to moles. And how do we do that? How do you convert mass to moles? What do you need to know, find, or calculate? The molar mass. So you might need the molar mass. And the volume has to be in liters. Okay, so the volume needs to be in liters. So that means you might have to convert milliliters perhaps to liters. And when you do that, you should know that the relationship is 1,000 milliliters is equal to 1 liter. So let's talk for a moment about concentration, molarity, and calculating stuff, okay? So we're going to do a couple of examples here, and the examples, again, aren't too tough math-wise, but I am going to show all of the steps because I do know that some of you really like to see the steps, especially with problem number 2. So like I always do, I'm going to take the time to identify my variables. So molarity, moles, liters, and I'm going to also put mass, which is grams, okay? So as I read this problem, the problem asks me to calculate the molarity. So it says, what is the molarity of a solution in which 125 grams of NaOH is dissolved in enough water to make 0.8 liters of solution. So the problem is asking me to solve for molarity. So the problem is asking me to solve for big M. And I have liters, but I don't have moles. So that tells me that my first step is I'm going to have to convert grams of sodium hydroxide to moles of sodium hydroxide. And in order for me to do that, we've already discussed that we need the molar mass. So I'm going to calculate the molar mass by saying there is 1 sodium times the mass of sodium, which is 22.99 grams. There's 1 oxygen times 16.00 grams. And there's 1 hydrogen times 1.01 grams. And when you add all of that business up, you get something like, I think it's exactly 40 grams per mole of NaOH. So again, my first step is going to be to convert grams to moles. So I'm going to take that 125 grams of NaOH and convert it to moles. So I'm going to put the 40.00 grams of NaOH on the bottom and the 1 mole of NaOH on the top. Grab my calculator, 125 divided by 40. The calculator gives me something like 3.125 moles of NaOH. And so this 3.125 moles of NaOH is going to actually be this part of my variables, right? So now I have enough information to solve for molarity. So I'm just going to move over one step and take molarity is equal to the 3.125 moles of NaOH over 0.800 liters. And so that's a pretty simple calculation, 3.125 divided by 0.8. And my molarity here is going to be like 3.90625. And then we have to assess significant figures as one does. So this is going to have 3 sig figs. This number here has 3 sig figs. So my liters, or my given values in my problem had 3 sig figs. So my answer should reflect that. That 6 will round that 0 up. So my final answer here is going to be like 3.91 big M NaOH. Now that tells a chemist and a chemistry student how much sodium hydroxide is in that given amount of water. It's like, it's like with the lemonade example, how much lemonade was dissolved in a given amount of water, right? So like in this case, 3.91 molar NaOH to a chemist and a chemistry student is like, that's pretty concentrated. There's a lot of stuff in there. Okay. That's what that should tell you. The bigger that number, the more concentrated it is. Yes, sir. The question is there a maximum to that number? And actually, yes-ish. So there is a ratio of how much stuff can be dissolved in a given volume at a given temperature. So this goes back to the solubility curve that we talked about yesterday. So that line on the solubility curve is essentially the maximum that can be dissolved at that temperature for that amount of stuff of water. So there is a maximum-ish. Okay. And it really depends on like some other variables. Okay. So yes. So what I want you to do now is go ahead and give this one the old GHS try here. Go ahead and give this one the GHS try. For those of you that are playing along, I've identified my variables if you want to compare. Okay, so this ended up happening in 2 steps, right? So step number 1, you had to calculate the number of moles that were present in this particular solution. And a common mistake that students tend to make with this style calculation is they somehow do the math. They don't quite do the math right. They end up dividing instead of multiplying, and that usually throws some people for a loop. So I took the time to show all of the steps here to kind of make sure that we know what we're supposed to do when we're supposed to do it. And I calculated 0.04375 moles of sodium sulfate dissolved in that 0.175 molar solution. I then went one extra step further and I converted mass to moles, moles to mass. And I got 6.2146. So the last thing we need to do is assess significant figures. Our given values in the problem both have 3 sig figs, so our final answer should also have 3 sig figs. That 4 cannot round that 1 up, so our final answer is going to be something like 6.21 moles of Na2SO4. Something in that ballpark. Questions about this one? Again, the common mistake that some students make is the initial math step, they end up dividing instead of multiplying. Yes? Is it moles or mass? You're right. Grams. Thank you. Good catch. This would be grams. Grams. Okay. Now, so that's part of today's lesson. The other part of today's lesson is dilution. Okay? And so anytime that you have a solution already and you end up adding water to it, it becomes less concentrated. When you make something less concentrated, we say that it is dilute in nature. Okay. Now, the next thing, what I'm trying to simulate here is that if we start with something called a stock solution. Now, in a chemistry laboratory, stock solution is a solution that's been pre-made of a known concentration. Okay. And then what we do is we can draw from that stock solution and we can take that stock solution and we can dilute it out. Sometimes when a pharmacist is preparing a medication, what they will do is they will get this medication and they get it in a bottle, and the bottle is like it's like super concentrated medication. Like they buy a lot of it in a tiny bottle, basically. And then what they do is they'll draw some of that out, and then they'll go over to a little water dispenser, DI water, and they'll fill it with DI to the right amount, and then they mix it up, and then that becomes the concentration that you need to take for your medication. Yes. It is annoying to do, but it doesn't kill people. So the issue then is that's kind of like what this is that was going on here. So in our stock solution, if I took out a 1 milliliter sample, so here's my that's a drop of this sample, so it's 1 milliliter, and I add it to another container and I dilute it up to a total of 10 milliliters. So I've got 1 milliliter of stock solution and 9 milliliters of water. I make a new solution that is significantly less concentrated. It goes from 1 molar concentration to 0.1 molar concentration. And if I take one more drop out of, that's a better drop. That's a beautiful drop. So I take one more milliliter out and of my new solution, and I put it in a new container and dilute it up to have 10 milliliters total. So 1 milliliter of solution and 9 milliliters of new water. I now make a significantly less concentrated solution. And we can do this all the way across here. And what really ends up happening, I don't know what that is. And what ends up happening is that, first of all, something that's really, really concentrated might have a specific color, but as you add more and more water to it, its color becomes lighter and lighter and lighter. And that's true. That's very true. But the other thing that's true is the concentration of the original stock solution goes down significantly. So if this stock solution at 1 molar was something that was very, very, very toxic to human beings, at 0.0001 molar, you might have no toxicity at all. Does that make sense? So that's something to consider. And what this process is showing here is something that we call a serial dilution. We start with an original concentration solution, and we continually dilute it out till we get the concentration that we want. Now, dilution equation. So there's a formula for this, so you don't have to keep doing the math over and over and over again. So there's a formula for this, which basically is M1V1 equals M2V2. M1 is the original concentration of the solution that you're starting with. V1 is the volume of that concentration that you use. M2 is the new concentration that you produce or you're trying to produce. And V2 is the volume that of your new diluted solution. So there's not a difficult thing to do math-wise, but sometimes getting the numbers in the right spot can be tricky. So let's do a few of these real quick ones. So we have M1, V1, and M2, V2. Now, when I read through this problem, what I'm going to try to do is help you to identify what number goes where, because it does matter. So the question says, what volume of 2 molar sodium hydroxide solution should be diluted to prepare 100 milliliters of a 0.5 molar solution? So this problem says we are making 100 milliliters of 0.5. So my V2 is going to be 100 milliliters, and my M2 is going to be 5 molar. And this time, the question is asking me, what volume will I need to use of my 2 molar NaOH solution? So we're really solving for V1 here. So in this problem, I'm going to go M1, V1 equals M2, V2. And so I'm going to take my original concentration, which is 2.00 molar. We're looking for V1. I do know that my new concentration is 0.500 molar, and my new volume is going to be, it's going to be 100 milliliters. So in this problem, we're simply going to divide both sides by 2 at some point. So Oops, that was ugly. So I'm going to take the 0.5 times the 100 divided by 2, and I'm going to get my initial volume that I got to start with, which is 25 milliliters. So it's going to be 25 milliliters. And that should make a little bit of sense. I wouldn't really imagine that I would need a lot of a really concentrated thing to make a less concentrated solution of the same type. Yes?
So how do you identify which one is M1 and B1? Like, is it just whichever is mentioned first in the problem?
The question is whichever one is. The question is how do you know what goes where? And part of it is just going to be practice, but part of it is going to be reading what what is actually occurring in the problem. Imagine yourself being a chemist, and you're like, what are my steps here? Okay, or imagine you're making the lemonade. Like, what if I replaced what volume of canned lemonade should I dilute to prepare 100 milliliters of like less lemonade-y goodness? So like it's about what the problem, like you're thinking about that in that capacity. So let's talk through this next one because that might help. Because this next one is a little bit trickier, but it's not too bad. It's totally doable. So M1, V1, and M2, V2. So in this problem, it says 100 milliliters of water. So like that's clearly going to be a volume, right? Is added to 500 milliliters of water, or I'm sorry, is added to 500 milliliters of a 0.1 molar solution. So this question says, what's the new concentration? So it's asking me what my new concentration is going to be. So when you think about things in terms of steps, one usually comes before two, right? When you're counting things. So in my head, new should be my M2. Okay. So that's what I'm going to be solving for. And then the original question says, so then that tells me that my original concentration is going to be the 1 molar. And then now this is just a matter of how the problem is worded. 100 milliliters of water is added to 500 milliliters. So that tells me that my original concentration is 500 milliliters. But my final concentration is going to be 500 milliliters plus 100 milliliters for a grand total of 600. Do you see what I did there? Hopefully. So now I have M1 times V1 equals M2 times V2. So I'm going to plug in what I know, which in this case is going to be 0.100 molar times my 500 milliliters equals M2, which I'm solving for, and V2, which is now my 600 milliliters. So in this problem, I'm going to divide both sides by 600 at some point eventually. And so that's going to give me 0.1 times 500 divided by 600. And I get a new concentration this time around to be somewhere around 0.0833 molar. HBr is M2. Okay. There's one more here, and you know what's coming next. The old GHS try. Yes. I did do significant figures for this. And the leading zeros at the front aren't significant if there's a decimal. So that's why I rounded it to 0.33 because everything else had 3. Okay. All right. You know what's next. You know what's next. Good old-fashioned GHS try. Let's do it. If you need a second to check your variables, This is where I'm at.
Can you talk about when it's one column why you add like a 250?
Yes. Okay. So the reason why I did this one the way that I did is that it says 250 milliliters of NaOH solution is diluted with 500 milliliters of water. So that tells me that I started with 250 milliliters and added to it. Okay. So my original volume was 250, but my final volume is 250 plus 500. Does that help?
Yeah.
Okay. So at this point, it was just simply substituting into the formula. So I solved for M1, and I ended up getting 1.05 molar sodium hydroxide. And that's your lesson for today. And your homework for today is to do worksheet number 3, which is a one-sider, I believe. Has anybody looked? I think it's a one-sider. It's 3 problems of molarity 3 molarity problems and 3 dilution problems. So there's that. And hopefully, as you're doing these problems, you will reevaluate how you make lemonade, because I haven't come up with a better way yet, other than to get frustrated. And hey, have a good day.